and we want to figure out the skier's speed at A. So this is definitely a problem. Okay, actually, here we're going to start at B. So U plus WNC equals U at A plus K at A. This is a interesting diagram where we're on an arc of a circle. I'm going to choose the lower location to be where y equals 0. And it really doesn't matter where you choose that location to be, but I think that'll make this a little bit easier. So that means at B, the potential energy is 0. There is kinetic energy there. I'm just going to throw in the letter m here. You'll see that it cancels out later. If you don't want to put in m, you can always find the mass of the skier by taking the weight 600 divided by 9.8, and that works just as well. Anyway, at B, it says her speed is 8 meters per second. There's no friction or any other non-conservative forces in this problem, so WNC is 0. And the U at A, there is some gravitational potential energy there. It's m times 9.8 times the y position at A. And I think that's the real trick of this problem, is figuring out what that is. We also need to find out, really the question in this problem is, what is her speed at A? So as I said, we're going to have to figure out the y position at A here. And we're going to have to do that using some geometry. So let me redraw this diagram. There's the radius when she's at the highest point, and here's the radius when she's at the lowest point. And what we really need to know, since this dotted line is where y equals 0, we need to know how high this is. What is the y position of the top of that radius there? So this takes a little bit of trigonometry. They show us that this is a 20-degree angle here. And they also show us that the radius is 20 meters. And so it would help if we knew this adjacent side of this right triangle here. So we can use a little bit of trigonometry for that. Since it's adjacent, I'm going to use cosine. So the cosine of that 20-degree angle is equal to the adjacent side divided by the hypotenuse, which is 20. And if you do the math on that, what you'll find out is the adjacent side is equal to about 18.8 meters. So this distance right here is 18.8 meters. Now the entire radius is 20 meters. So if we take that entire distance of 20 and subtract the 18.8, we will get that little y position that we want, and that's 1.2 meters. So yeah, the leftover right here is 1.2 meters. That's what we need to put over here in our Uckwuck equation. And now we only have one unknown, the speed at A, because the masses do cancel out. There's a mass there, there's a mass there, there's a mass there. And when you put that in your calculator, you should end up with about 6.4 meters per second as the answer to part A. For part B, they ask what minimum speed can the skier have at point B and still coast to the top of the hill. So really this is just another Uckwuck with slightly different values in it. Once again, at B, the potential energy is 0. We're trying to find out now what minimum speed is needed at B. So I'm going to leave the speed at B as a variable. No work done by non-conservative forces. There's no friction. Same potential energy at A, m times 9.8 times 1.2. But now the kinetic energy at A is 0, because if you're just barely going to make it at A, it means that as you get to point A, your velocity is going to become 0. Masses cancel out again. So the speed at B, if you do this on your calculator, you should get around 4.9, somewhere around 4.9 meters per second. And that is the answer to part B. Part C asks us whether these two answers will change if the weight of the skier changes. And well, you can see very clearly the answer to that is no, because in both cases the mass canceled out.